Welcome back. In today's video, we want to go over a brief introduction of the difference amplifier. So the difference amplifier is a combination of the non-inverting and inverting configuration combined into a single op-amp circuit whose output is the difference, or whose output represents an amplified difference between two input signals. Our input signals are V1 and V2. So our op amp operates in the linear region because we're dealing with ideal case. So we can use superposition to find the expression for V out. We can do this by setting, and before we do that, in ideal case, by virtual short, the voltage at V plus can be assigned to the voltage at V minus. We know that I plus is equal to I minus, which is equal to 0 volt. In our case, I'm going to leave a question sign here because we're going to do something to the op amp circuit, which is going to change V plus equal V minus, which equals to 0 volts. So first thing to do is to set V1 equals to 0, find the expression for V out, set V2 equals to 0, find the expression for V out. So we're going to call the first expression for V out X. So V1 is equal to 0. We know that by virtual short, in our case, V plus is equal to V minus, which is equal to 0. Let's write that here. 0 volts. We can then, by previous knowledge, we know that by setting V1 equals to 0, we then get a difference or a inverting amplifier configuration, which we know the expression for V out is going to equal to, and remember we're going to call that V out X, is minus R2 over R1 times V2. If we then set V2 equals to 0 volts, V plus is now equal to V minus, which is now equal to V1. Because here we can see V1 is directly connected to V plus. So the voltage at V plus is equal to V1. So now the expression for V out, and we're going to call that Y, is then equal to R1 plus R2 over R1 times V1. And that is the output voltage of the non-inverting configuration op amp. So if we add both of those together, we then get the expression for V out. However, as you can see, our expression for V out has multiplication factors of different values. See, the multiplication factor multiplying V1 and V2 are not equal. So we can remedy this, or we can improve our difference amplifier by adding a voltage divider network between V1 and V plus. So if we can attenuate the voltage at V plus, we can then fix the attenuation factor or the multiplication factor for V1. This can be done by adding our voltage divider network, and this works because I positive the current entering the V plus terminal is equal to 0 amps. That should have been volts, that should have been amps. So we can add the attenuation network. V plus can now move here. So this is R1 and this is R2. As we said, this can work because the current entering the V plus terminal is 0 amp. So now, if we look at our first expression, when we set V1 equals to 0, the voltage at the plus terminal does not change, so it keeps at 0 volts. So our first expression for V1 equals to 0 is equal to the same thing. However, our expression here for V2 equals to 0 will change. And this will change because V positive, the voltage at V positive now becomes the voltage across R2 by voltage division. So as you can see, V1 is now attenuated by the configuration of resistors. We can then go ahead and input that by saying V out Y is now equal to R1 plus R2 all over R1 multiplied by R2 over R2 plus R1, which we see those cancel, times V1. And now we see that we have R2 over R1 times V1. So our multiplication factor for V1 now changes to the ratio of R2 and R1, which is the same for when V1 is set to 0. So this now becomes, V out now becomes R2 over R1 times V1 minus R2 over R1 V2. And as you can see, V out is equal to R2 over R1 multiplied by the difference between V1 and V2. So, as stated earlier, that the difference amplifier is a combination of the non-inverting and inverting configuration into a single op-amp circuit whose output represents an amplified difference between two input signals. So an amplified difference between two input signals, here's our amplification factor, and here's the difference for two input signals. So as we said earlier, the voltage divider attenuates V1 by our network of resistor. And then this relation works. So before the and then, this relation works because the current I plus is equal to 0. And this relation, or this, will always work if the attenuation network R2 over R2 plus R1 is equal to the, so here's our attenuation network, and here's our feedback network. So this difference amplifier will only work if the following is true. So this is our attenuation network, and this is our feedback network. Note that for the attenuation network, this can also be true if we had R4 over R4 equals to, well, not equals, plus R3 is equal to R2 over R2 plus R1. So that means the resistors doesn't have to mean the same, have to be the same. And this can be simplified to basically just saying that if R4 divided by R3 is equal to, my bad, that should be R3 divided by R4 is equal to R1 divided by R2. If that condition is met, then the difference amplifier will operate correctly, and thus we can use the attenuation network to fix the multiplication factors for V1 and V2. And that's it for this video. See you in the next one. Bye.